Hello everyone, this is Nick. Welcome to a new session of MIST102. In this session we'll be talking about recurrent neural network. And recurrent neural network is a more advanced topic in machine learning. In this session it doesn't require you to have a good background in math, calculus, and machine learning. Just try to understand the concept and how the model works. I will be making a lot of analogies so that it will help you to understand it. And at the very end, there will be a small quiz post in our channels. So try to complete it as a good exercise and practice. It won't be hard and it will be good for you. Okay, I really hope that you could enjoy this session, and let's get into it. So in today's session, we will be first giving a recap on CNN. So convolutional neural networks. This session last time is covered by Hitov. And then we will be talking about sequential data and memory, which are the focus of today's session. And then we will be talking about how memory works for human beings. I think this is very important if you want to try to understand the recurrent neural networks, because a lot of us actually neglect that. Architecture of recurrent neural networks actually come from how memory works for human beings. So in this section we will understand how our memory works, and it can help us to understand RNN better later. So after covering the real recurrent neural networks, I'll be talking about some problems with RNN and a solution, LSTM, GRU, and finally we will be coding in Python using the PyTorch library to show you that how to actually implement RNN and what kind of problems we can solve with it. So from last time, we know that convolutional neural networks is very powerful, especially in dealing with data like images, right? So from last time we know that pictures can be represented as an array of pixels. And we can feed these pixels into the model and give us an output on whether to classify a result. For example, in this animation, it's classifying the MNIST data set into the numbers, into the figures. And we also talk about the components of CNN, like the kernels, the stride length, and we can use techniques like padding and pooling to make the performance better. Right? And if you are not familiar with this, you can check out the last session on it. And I want to first mention what our CNN is good at. We can use image classification as an example. So if we had an input, that is one single image consisting of a lot of pixels, and the output is a probability prediction of each class. So if we think this way, only one image is processed at a time, and the network forward passes once to get an answer. For example, if you have a collection of images, but every time you can only feed one picture, well, one image to the model, and the model just forward pass once, right? And you get a result. Whether you do a classification problem or regression problem, it'll give you a result straightforward, right? And next time you're feeding another image, it gives you another result. So it doesn't matter the order you feed into the data, right? You can have random sequence of images feeding to the model, and the model will give you identical results for each image. So what if we have a sequence of data? So sequential data, a series of data where order matters. For example, the sound, text, DNA structures, or videos. So videos are actually a sequence of images, right? Consisting of frames of pictures, and also stock market price, right? The most common case is that the data is changing through time, and because the sequence of time cannot be messed up, so the sequence of data should be in some certain order. We cannot make it random, and if we make it random, then the data loses its meaning, right? But how do we deal with them if the order matters? Think about CNN. Every time you passing one data, and next time you passing another data, right? The model cannot figure out the connection between these two. So two computations are totally independent. All right? The model cannot have a memory or some things like that to find out the connection between each input. And for each unique input, you get a unique output. That's it. So what do we want? We want an architecture that can take in variable-sized sequential input. So variable size may mean that, for example, I have a paragraph, right? A sequence of words or characters. It could contain maybe 200 words or 300 words, and the model can process that. And it can remember things over time. Using the paragraph example once again, the sequence of the words actually matter. So when the model is processing the next word, it should probably remember the first few words or all the way toward the first word, so that it can figure out the meaning of the whole sentence and figure out the meaning, the coherency throughout the whole paragraph. But you may probably remember this 3D CNN from last time, right? This kernel has an additional dimension, which is the depth, right? To make it a 3D kernel, and the kernel traverses the depth of the input data. So for example, if we have a video, you can think of it as a stack of images, right? It has depths, which are frames, right? And this kernel is 3D, so it every time the kernel computes, it's computing the connections and features through time as well. But what this can't do is it cannot figure out the connection between the last one and the first one, because the kernel has some certain size. It can only compare the neighboring frames and figure out the connections. It cannot remember the first frame when it's processing the last few frames, right? So this is a disadvantage of 3D CNN, and we really want an architecture which can remember all the way to the first frame, right? When we're processing the last frame. So of course, the memory is the most important thing, and it's hard to keep the memory in the model when the model can only do forward passing, right? So if the model can somehow temporarily store the memory of data it processed, it can react to a sequence of data where order matters. If the model can remember the inputs it processed earlier, then it may have a different compute result when it's processing the input later. Using the goldfish as an example, if you believe it, right? Goldfish have let's just assume that a goldfish has only 10 seconds of memory. It can not remember things happening 10 seconds before. So for this fish, it's only processing the states or data that it receives right now in the current time. So it cannot make some comparison with what happened in the past. So it's just like a very simple model, a simple machine. It can only react to what's happening right now and dealing with the current situation. And if it has memory, then it could react to something that might happen before and make a different reaction to that. Let's see how scientists understand or interpret how memory works in a human brain. So most people refer to memory as something that they possess. However, the expression "I lost my memory" is technically incorrect. Memory doesn't exist in the same way that a part of our body exists. It's not physically present. Rather, it is a concept that refers to the process of remembering. At the most basic level, memories are stored as microscopic chemical changes at the connecting points between neurons in the brain. And we've talked about brains and neurons in MIST101 when we show the difference between biological neural network and artificial neural networks. And we know that this structure exists in our brain, and there are billions and billions of it to form our brain neural networks, and it makes us intelligent. And the machine learning scientists essentially just copy that structure in our brain to form the artificial neural network. Also consists of millions, maybe billions of neurons, right, to make the model intelligent as of machine intelligence, right? So it is comparable between a human brain and an artificial neural network, also for memory. And in this case, we say that memory doesn't exist physically. Well, you may have a different opinion that as a human, we could write something down if we don't want to remember them, and write it on a paper. And in computer, right, we could store them in a hard drive so that the information doesn't get lost. But when we're processing the information, so in the process of remembering something, we doesn't really have that as a physical. So it's just a bunch of chemicals in our brain. And also in the neural networks, when it's processing the information, it doesn't store the information inside a hard drive or something. It just computes loops inside it. And this is very similar between also how memory works inside a human brain and how memory works as of recurrent neural networks. Of course, there are a lot of types of neurons in the nervous system to help us, and there are also different networks inside a big neural network to act as different functions. So there are certain steps involved when a memory is processed, and we are going to see how it happened. So the first step is called encoding. Encoding is a biological phenomenon that starts with perception. Consider, for example, the memory of the time when you met a personal idol. At that point, your visual system picked up how much of a dynamic personality they had in real life. Your auditory system picked up the sound of his or her voice. Your olfactory component probably even registered how the person smelled. These sensory cues are largely responsible in informing our perceptions. And you know what I'm talking about right now when in artificial neural network. That is our input. We can have many sources of input, right? And back to the human brain, each of these separate sensations travel to the part of our brain called hippocampus, at the highlighted area here, which integrated these perceptions as though they were a part of a single experience. The hippocampus is responsible for analyzing these various sensory inputs and deciding if they are worth remembering. If they are, they may become part of your long-term memory. Although memory starts with perception, it is encoded and stored with the help of neurons. Neurons are the basic means of information transfer within the nervous system. This information travels through the nervous system by communicating with other neurons via an electrochemical process. And once memories are encoded, they are transferred to either the long-term memory or the short-term memory. This transfer is a part of a memory stage, which is the second step in the formation of memory. In neural networks, there's also one kind of network called encoder. Right? There are encoders and decoders. So for encoders, the shape is like it's this shape. So the first few layers, it will have a lot of neurons, and into the deeper layers, it will have fewer neurons. So at the very end, right, the output is very little, like only a few. So in this way, you have successfully encoded the data through a forward pass because you have lots of inputs, right? But at the end, you only have a few outputs. In this way, you encode, and it saves the space, right? Now, in the second stage, it's called memory storage. This is very interesting. There is no need for us to maintain every perceived detail of life in our brain. The different stages of human memory function as a sort of filter that helps to manage the flood of information we are confronted with on a daily basis. So as soon as we intercept certain data or note an event, the information is encoded into the short-term memory. The short-term memory has a fairly limited capacity. It can hold about 7 items for no more than 20 or 30 seconds at a time in our brain. Once this information is processed, 2 different things can happen. The information can be lost, or it can be transferred into long-term memory. So there is a process that our human brain will decide whether this short-term memory will be forgotten, or it will become a long-term memory which we will be remembering for a very, very long time. And long-term memory is a part of our memory storage system that has an unlimited capacity to retain information, right? Including conscious and unconscious memory. Okay, now, so up to this point, the steps in the formation of memories have been mentioned, but how do we recall these memories? So when you want to retrieve a particular memory, you have to reach out to the unconscious level of memory storage. This data is transferred to the conscious level at your will. So you can try to understand this diagram yourself, but the most important thing is that when you want to retrieve a particular memory, you have to reach out to the very deep level of your memory and bring it to the shallow layers and use it. So after talking about how memory works inside the human brain, we want to talk about how to actually build a recurrent neural network and compare it with the feed-forward neural network. And RNNs and feed-forward neural networks get their names from the way they channel information. We talked about feed-forward neural networks in MIST101 a lot. Its architecture is the most basic in all ANNs. So up to CNNs, all the architecture we've seen is feed-forward neural networks. So in a feed-forward neural network, the information only moves in one direction, from the input layer through the hidden layers to the output layer. The information moves straight through the network and never touches a node twice. Feed-forward neural networks have no memory of the input they receive and are bad at predicting what's coming next, because a feed-forward network only considers the current input. It has no notion of order in time. It just can't remember anything about what happened in the past. But in an RNN, the information you can see here cycles through a loop. When it makes a decision, it considers the current input and also what it has learned from the input it received previously. And in this demonstration, right, if we unfold the RNN cycles, it will become a plane structure, although it's actually 3D because each unit here is a complete neural network. So if we give different inputs through time, all of the outputs in the hidden layers, right, will pass through itself in the next iteration, and also again pass through itself into the next iteration, along with the new inputs here. So this is a way how we unfold RNN to show that, okay, it's actually looping cycles, but we extend it, right, in making copies of itself, so that we can directly see how this network extends. Another good way to illustrate the concept of recurrent neural networks memory is to explain it with this example. Imagine we have a normal feed-forward neural network, and give it a word sequence. How does this work as an input? And it processes word by word, right? This is impossible for a simple feed-forward neural network to predict which word will come next, because it doesn't have the memory of everything before. Each forward pass is independent. A recurrent neural network like this, however, is able to remember those words in a sentence because of its internal memory. It produces output, copies the output, and loops it back into the network. So simply put, recurrent neural networks add the immediate past to the present. Right? Therefore, RNN has two inputs, the present and the recent past. So like this, at t equals 0, so initially we have input how. Of course, it can process it through a forward pass, but it also passes the output to itself in the next iteration. And this set of neurons here will process information passed through itself from the previous iteration, and also process the real input in this iteration, which is the word does here. So this is important because the sequence of data contains crucial information about what is coming next, which is why an RNN can do things other algorithms can't. A feed-forward neural network assigns, like all the other deep learning algorithms, a weights matrix to its inputs and then produces the output. Right. Note that RNNs apply weights to the current and also to the previous inputs. Furthermore, a recurrent neural network will also tweak the weights for both through gradient descent and backpropagation through time. So if we're actually training this neural network, by the time we input work here into the network, it will not only update the weights in this level, it will also backpropagate to the previous levels. So all these structures will be changed. So in a common programming frameworks like PyTorch, backpropagation is automatically taken care of. So there's no need to worry about the math if you just want to code. So you just need to know that when you in the later iterations, right, it will update all of the weights back to when it first input in the first iteration. But what about the output, right? There can be many combinations of input and output. For example, we can have 1-to-1. This is just a very simple feed-forward neural network. We could have 1-to-many. So we input only once, and the model cycles through itself to produce multiple outputs in a sequence. And in this scenario, we call it a generation. So this kind of architecture can do generation tasks. For example, we can just write a simple number, and it can generate a sentence for us. And we could also have many-to-one. So we input at each iteration a sequence of data we have, for example, a sentence or a paragraph. And it cycles through itself and finally gives one thing. It might be a prediction, it might be a classification. So we might classify this sentence to some category we want. And of course, we could have many-to-many. So we not only input at every iteration, we also get output every iteration. And the order of the output also matters. So this is like something like text prediction or translation tasks, where inputting maybe one language at the same time is translating to another language, or just as an example. So we know the input and output here. The green boxes in the middle are called the hidden states. And this is the most important part in the RNN architecture, because these hidden states, they will process the information from the inputs and from the previous iteration together with, and it will produce this output. So these hidden state structures are what we want to focus next. To explain it using an example, right, we can once again have a sentence, so a sequence of words, a series of words, and we're using the many-to-1 as the example. So after the initial state, we start to input the words into the hidden states, and the hidden state is updated based on a previous hidden state and the input. Note that the arrows at the bottom, this indicates the information flow direction. So it not only takes the input from the previous state, it also takes new inputs. And it will continue to update the hidden states based on previous hidden states and the input. And as we input all of the words in the next few iterations, it continues to update the hidden states until we run out of inputs. And then we use the last hidden state as an input to a prediction network. So think about this. This last hidden state contains all of the information from the previous inputs and the previous hidden states. The result of the process from all the previous hidden states. So this, the final hidden state, contains the memory, right, of everything before, and the memory comes in a sequence. And we pass this encoded information into a prediction network, so we can get a prediction, as our many-to-1 example. So each hidden state we talked before is an RNN layer, and it could be represented as this graph shows. So the yellow box is a neural network layer, and the 10H here is the activation function it uses. So 10H function is typically used in all of the RNN layers, and the arrows here, right, it means vector transfer, but it can also concatenate or copy itself. So for example, from the last hidden state, the information passed to this RNN layer, but it concatenates with the current input in this cycle, and together they pass into this neural network, and the output of the neural network, of course, it will goes to the output, and the same thing will also go to the next RNN layer in the next iteration. And there are problems with RNN, and I want to explain this using the 10H function like this here. There are two major obstacles that RNN has to deal with, but to understand them, we first need to know what a gradient is. A gradient is a partial derivative with respect to its input. Just think of it like it measures how much the output of function changes if you change input a little bit. So if we change the input a little bit at the point, how much the output changes. So we can basically think of gradient as a slope of the function. The higher the gradient, the steeper the slope, and faster the model can learn, because the model learns through gradient descent. But if the slope is 0, the model stops learning. A gradient simply measures the change in all weights with regard to the change in error. So for example, at the points here, or even far here, the slope is almost 0. And at the point here, when x equals 0, the slope is the steepest. So we know the gradient is 0 here, and the gradient is very large here. This would cause the problem first because the RNN structure is very, very large and very, very long. So for example, the diagrams we see before when we unfold an RNN, if we have inputs like hundreds or thousands of iterations, then the model is very, very long. That will cause some problem. The first problem is called vanishing gradients. Vanishing gradients occur when the value of the gradient are too small and the model stops learning or takes way too long as a result. So if you have a very small gradient calculated at the final few iterations, and you want to update the weights at the very, very first iterations, it will take a very long journey to pass all the way back, and this gradient is already very, very small. So by the time this gradient by the time this gradient multiplies all the way to the first layer, it will be nearly just 0. So when the input goes to the final few iterations, the first will not be changed at all. That's just a simple way to describe what's vanishing gradient. And on the contrary, we could also have exploding gradients. So it happens when the algorithm, without much reason, assigns a stupidly high importance to the weights. So at these points, right, the slope is very steep, and when it propagates, right, it multiplies large weights all the way before. So it will be so the layers at the beginning will be updated largely. However, this problem can be solved by truncating or squashing the gradients for exploding gradients. So vanishing gradients is the main problem. And the solution to vanishing gradient is the long short-term memory. So as a modified version of a normal RNN layer. So long short-term memory networks are an extension for recurrent neural networks, which basically extends the memory. Therefore, it's well suited to learn from important experiences that have very long time lags in between. I'll explain how it works. So the units of an LSTM, so long short-term memory, are used as building units for the layers of RNN, also often called an LSTM network. LSTMs enable RNNs to remember inputs over a long period of time. This is because LSTMs contain information in a memory, much like the memory of a computer. The LSTM can read, write, and delete information from its memory. So when we talk about the problems of vanishing gradient, it means that things happen long before will not be updated correctly, and it takes a long journey towards the very end. So it does not remember things effectively when there are a long way in this structure. So for LSTM, it can retrieve, remember, or even delete the unuseful information. So you can remember all the way back to the first few iterations so that you have effective memories. And to explain how it works, this memory can be seen as a gated cell, with gated meaning the cell decides whether or not to store or delete information. So whether these gates open or not, based on the importance it assigns to the information. The assigning of importance happens through weights, which are also learned by the algorithm. This simply means that it learns over time what information is important and what is not. In an LSTM, we have 3 gates, which are the input gate, forget gate, and output gate. These gates determine whether or not to let new input in, delete the information because it isn't important, or let it impact the output at the current time step. So in this diagram, there are 3 gates together affecting the flow of the information. If we break it down arrows by arrows, this would take a long time to fully comprehend, but let's just try to understand what's happening in this through these gates. So first, the new input comes into this LSTM, right? It copies itself into the 3 gates. Now the 3 gates have the information of the input, and the 3 gates will use this input to decide whether this gate will open or not. So if the input gate, this is also a network, right? It uses the input information to decide if the input gate is open. Right? If it opens, then the input, passes into the main network. And after the main network processes it, right, there's also the forget and output. So let's first look at the output gate first. So the output gate takes the processed information and also the original input together to decide whether to open this output gate. If it's open, then this processed information will be passed to the next LSTM. If it's not, then this is just the end of story. This unit just ends because this information doesn't get passed through. And there's also the forget gate. The forget gate also takes in the original input and the processed information to together decide whether this processed information is useful. If it's not useful, this forget gate will be closed, which means that the information doesn't get passed to itself in the next iteration. So it's just like forgetting. And if the forget gate is open, then this information gets passed to the next LSTM. So it gets extended. So after understanding how the each gate work in this LSTM, we get a sense that these gates can control whether this information get passed to output or to next iteration. So unuseful information will be just deleted right here, and so the model doesn't take doesn't store a lot of information, and its computation is saved. So useful information gets extended all the way to the end, but unuseful information will be forgotten immediately. The gates in an LSTM are analog in the form of sigmoids, which is this red function we see in this graph. It ranges from 0 to 1, and so 0 means the gate doesn't open, and 1 means the gate do open, so it allows the information to pass through. And also this would affect the backpropagation as well. So the problematic issue of vanishing gradient is solved through LSTM because it keeps the gradients steep enough, which keeps the training relatively short and the accuracy high. There is also a unit called the gated recurrent unit, the GRU. So it is a variant on LSTM and is much simpler than LSTM. Again, this is a diagram. It also has some gates, but it's simpler in structure. It merges cell state and hidden state. So a simpler version of LSTM. And we come to the summary of all of the recurrent neural networks and LSTMs. So recurrent neural networks are more suitable for sequential learning, relevant to other simple feed-forward neural networks, and they were historically hard to train. They're good for capturing recent information, but difficult with long-term dependencies, as we described the vanishing gradient previously. And to solve the problem of vanishing gradient, LSTM and GRUs are invented so that these layers can replace RNN so that the model is easier to be trained. But can we have something like a deep RNN? So everything extends deeply, and also it could be combined with convolutional neural networks or other types of networks. So think about the case of video processing. So we have an image of hundreds of pixels. That is too much for an RNN or LSTM to take. Then there will be millions of information to be processed. So we could first pass it through a convolutional neural network to extract the useful information within those images, within the single frames. And we pass the encoding information into the RNN or LSTM so that information gets processed more effectively and quickly. And finally, we get some output that we want. So basically, you could do a lot more tasks with RNN and LSTM to deal with sequential data, but you could also combine with other networks like convolutional neural networks to build a more powerful network. This is just an introduction to recurrent neural network, but of course you could explore more, and there are definitely more tasks that can be achieved. And that's all for the lecture part. Thanks for listening up to this point, and we will be going to the coding session.